So what I did to make this first simulation is I used the Xbox Kinect sensor and recorded the data coming in from the Kinect sensor in MATLAB to track my wrist motion, and then I attach a coordinate frame to my wrist and we make the robot mimic that motion. So we have a workflow to go from Kinect sensor to the robot, and MATLAB will output the file that I'm about to run. So if we queue this up here, run button. So this is, it was at the end of its trajectory, now it's going to start. So it just started. So this is the trajectory that I had traced out with my wrist with the Kinect sensor. And this is running at about a quarter speed or half speed. I can't remember what speed the teach mode runs on, but it's a lower speed than I was actually moving at. So that's why it's so slow. These are the functions that I've been working on creating. The skeletal tracking Connect takes the data from both cameras in the Connect and stores the wrist orientation and position. This wrist H function creates the transforms that I need. This smoother function smooths out the trajectory, so that the Connect is a noisy sensor, and the robot would be chattering all over the place if I didn't do this. So I spline fit the trajectories that we get so that they're nice and smooth, and the robot isn't having a seizure as it moves through its motion. And then this scale path to robot takes and blows the simulation up so that it's the right size for the robot workspace. And you can change the parameters for scaling inside of here, but you have to be careful because this doesn't right now have knowledge of what the robot's work volume is, and so you can make it do things that the robot can't do. So you have to be a little careful when you play around with that. And then this move-j compile function writes the rapid code file that'll actually run on the robot. And so right now I should be able to run this skeletal tracker and for however long I want, and it should output the rapid code file. So let's see if it works. It's so Connect is logging data, and so I'm just going to do some kind of like simple wavy motion here for a few seconds, and now it's going to trace out that path that we set. And that's the whole thing. It ran without error that time. So this is the first trajectory for the box animation. The orientation of the end effector here is a little skewed, so take it with a grain of salt. I've done 30 seconds here because it was hard to capture the motion that I wanted. With 10 seconds I couldn't get the timing right, and so I did 30 seconds, so just chop out whatever you need. And make sure you tell me the frame number. So here we go. So it's going to move back to its starting position. Go. So I have the digital input routed from this little board that I made to the robot controller, and when I push a little button on this board, it's going to trigger an interrupt on there that's going to tell the robot to move, and that same button press is going to be fed into the computer to start the video. So if I hit the button, the robot started and this little video window starts at the same time. Yeah, so I have the computer set up with max jitter that'll run the projection, and the robot set up so that it'll take a signal from the Arduino, and the max jitter will also take the signal for the Arduino. So when I push a little button, it'll trigger the projection on the computer and it'll trigger the robot motion at the same time. Now there's a little delay in the robot that we have to figure out. But that should be pretty easy. We can program that into the jitter part. So when I push the button, it moves. All right, you ready?
Ready.
I'm gonna go in 3, 2, 1, go. Ready?
Yep.
1, 2, 3. That's pretty close.
Do it one more time. That was good. Perfect. Seems like when it has a little resting, it does better.